Hello everyone, I'm Sashank. I'm from College of Engineering India and Anna University, India. I'll be presenting a paper, Intelligent Vision-Based Malware Classification using Quantized ResNets. It's co-authored by Rahul Chitaraman and Soumya Sanagavarapu. In this section, I'll be dealing with an introduction as to why malware detection is essential. Malicious software or malware are designed intentionally to be harmful to the system of programs or applications on a computer belonging to a user. These can infiltrate system security and gain unauthorized access for exploiting any programmable device, service, or network. A/B Test Institute evaluates and rates both antivirus and the security suite software for Microsoft Windows and Android OS. It registers over 350,000 new malicious programs or malware and potentially unwanted applications PUA each day. Over the last decade, the number of total malware detected every year is increasing, with 1.2 billion malware detected in 2021, as seen in the image. So malware detection is a branch of computer vision that aims to detect similarity in malware code variants. We use vision-based analysis of code compared to traditional approaches of analyzing just binaries of code because it does not require static assembly or execution of binaries. It identifies the particular texture with respect to each class of malware. To use vision-based analysis, we have set up ResNets. ResNets are classes of deep convolutional neural networks, which involves feature extraction and selection, parameterized forget gates, residual blocks, as well as weight sharing. The ResNets are unique in the sense they prevent the vanishing gradient problem in deep convolution neural network. So but the disadvantage of ResNets could be the heavier weight based on the number of parameters present within the ResNet architecture. To solve this, we use deep learning quantization. This involves reducing the precision of trained weights to reduce the amount of memory, computation, and energy bandwidths. This is performed by approximating the floating point numbers by using a neural network with low bit width numbers. System design. So we take our original ResNet model and apply quantization to create a compressed model. The quantization involves quantizing the layers as well as the activation function, and the layers could be quantized as weights as well as biases. So the dataset which we have used in this paper is the standard image dataset. It has a total of 9,339 images across 25 classes of malware. Each malware executable is represented as a grayscale image by converting the binary files of the malware into 8-bit integers. These are then reshaped to form a 2D matrix of decimal representations to form an image. So the classes of malware executables are shown in the given figure. So we use a quantization scheme for quantizing both the layer weights as well as biases. So first, we decided to use just ceiling function or floor function as seen on figure 4. We can see that the ceiling function, the disadvantage of using just a ceiling function or a floor function is that most of the values for lower bit numbers, such as bits of 1 or 2, are approximated to 0. This results in a loss of information. So instead, we decided to overcome this by using a quantization function which is taken as a combination of ceil and floor function as seen in the given equation. This quantization results in an accurate description of the values where each value is approximated to a finite interval. So quantization is the process where every value which is given to the quantization function is approximated to a given range, which is known as del x. And this results in lesser amount of memory requirements required to process this information. So activation function, we use ReLU as an activation function in the hidden layers. One of the ways of quantizing is the quantization of the activation function itself as seen given in the equation. It is quantized with the number of bits available b and the values are mapped between 0 and 2 power b minus 1. Any value greater than 2 power b minus 1 is passed to the function should be clipped first to fit the interval specified. And to quantized forward propagation, in addition to quantizing the layers, weights, and biases as well as activations, we also introduce a quantization factor, which is a scalar parameter phi. This is to improve the learning rate of the network. First, the weights of the network are scaled between -5 and 5 as seen at W bar. Then the quantization function is rewritten as 5 star the weights into the forward propagation value of the previous layer, which is L minus 1, plus the bias. We can see that the weights as well as the bias as well as the activation function are the quantized functions introduced in the previous section implementation. So the data set which we have used comprises of 25 classes of malware, and the percentage distribution of the classes across percentage distribution of images across the classes are given in the image. The data set is first split into a train test ratio of 80 to 20 with 7,481 images in the training set and 1,858 images in the testing set. So this is the ResNet module. This is a standard ResNet module, which has 2 parameterized and 1 non-parameterized layer. This results in a total of 3 different types of layers, which is frequently used within the ResNet module. The batch normalization and convolution layers are parameterized. Only the parameterized layers can be quantized. So these 2 layers are quantized, and then with max pooling layer, which is not parameterized, is used as such. We have the layers are grouped into 6 blocks, each having a quantized convolution layer, quantized batch normalization, and max pooling layers. This is a standard ResNet 50 architecture. Training parameters. The constructed ResNet module is trained for 15 epochs with categorical cross entropy as the loss function. We use ADAM optimizer with a learning rate of 0.001. The size of the input images are taken as 64 cross 64, with the batch rates also being 64. The bit representation adopted for the quantization functions are 4-bit representations. Results and analysis. We have trained the model over 25 classes for classification. We have trained it for 15 epochs, and we can see that the accuracy of the epoch 15 is 99.16%, and the loss is 0.0238. The training of the model is stopped to ensure that there is no overfitting of data. This is the overall classification matrix of the quantized ResNet module. It can be seen that the true positive rate and the true negative rate are high at 90 and 99% respectively, whereas the false positives and false negatives are very low at 0.02 and 0.10%. The performance of the model can be seen in the given figure. The accuracy of the model reaches 96% with the precision and recall of 90%. It can be seen that the effort score is 89% and the coherence kappa score is 95%. The AUC curve of the quantized ResNet model is given at 99.8%, indicating high performance of the model in distinguishing both classes. ROC curve plots the parameters of the true positive rate as well as the false positive rate in the X and Y axes. The actual shape of the ROC curve is determined by how much overlap the two distributions have. The area under the curve is equal to the probability that a classifier will rank a randomly chosen malware class instance higher than another randomly chosen class instance. That is, one particular class is ranked higher than the other malware class and vice versa. So we compare the usage of just a plain ResNet model with the quantized ResNet model. It can be seen that the number of parameters, the number of trainable parameters of the quantized ResNet is slightly lesser, but the model size is lesser by almost 7 KB. We can also see that the loss of the model decreases from 0.15 to 0.02, which results in a decrease in loss from 15% to 2% in just 15 epochs, which shows that quantized ResNets have a higher precision while training the network. We have compared the performance of our model with existing state-of-the-art architectures, and it can be seen that our model performs best with an accuracy of 96% compared to the other models. Conclusion. Classification of malware is to understand their purpose and intention on the system files. We can classify malwares by converting them into a visual representation of their binary code. And we can use a deep learning architecture and perform computer vision-based identification of the texture of these images. This results in no static disassembly or execution of binaries, which is highly important as malwares in their binary forms can be dangerous. We have used a standard ResNet architecture and have applied quantization functions to increase the precision as well as to reduce the number of parameters and weights of the network. Quantization involves estimation of a given value based on bit representations between a range del X. The efficiency of the quantized module is evaluated with respect to time, space, and computation, and the performance of the model is compared with existing state-of-the-art architectures. As future works, the constructed malware classification framework handles 25 classes, which can be expanded to accommodate more existing malwares for their real-time application. The model can be further optimized by reducing the number of parameters and the size of the model by using deep neural architectures such as VGGNet or ImageNet. By using pre-trained weights in the network, we can optimize the size of the model by using transfer learning. This can result in deployment of this model in any system application. We are grateful for the chairs of IEMCON 2021 for giving us this opportunity to present our paper. We welcome any questions. Thank you.